Right, thank you everybody for coming on such a short notice. So I understand this is the end of the semester, it's the holiday seasons, and everybody is like in the holiday mood. But I really appreciate you still be coming to hear about this talk. And yes, it's a short notice. We don't have many chances to come into the East Coast. We're stationed in China, so and we actually was planning to brought that our Sora platform with us, but it just a couple of days ago we found out that we actually brought the wrong car. So this scratch I had. So it's like we're not able to show you anything this time, but hopefully the next time
Sure.
we have a better plan. We can show you that again, and hopefully we'll be able to have some arrangement and make some of the Sora systems there into this lab.
Sure.
Okay, so with that, talk about our work. Before that, let me introduce the lab. Many of you are probably not familiar with. It's the Microsoft Research Asia's, one of the 6 Microsoft Research labs around, for the Microsoft company. So it's stationed in Beijing. So it's now into its 12 years already. About 200 researchers in all different areas. A couple of years ago, the MIT Technology Reviews called us the world's hottest computer lab. So the wireless and networking group have about 10 full-time researchers, divided into about 3 research areas. There's 2 big ones. One is focused on data center networking and cloud computing, and then there's one on software radios and wireless networking research enabled by software radio. And we have a small project on mobile systems. Besides the full-time researchers, all year long we have about 15, somewhere between 10 to 15 interns. We try to do the best research as we can, and we have the inspirations and ambitions to become one of the best CS computer science networking research groups in the world. So for the past 2 years, we have some actually good productivities, a lot of sitcoms and movie-com papers, and won some best paper awards, best demo awards in these top places. So we probably be one of the best networking groups outside of US today. So we still try to grow, and we're hiring for researchers and interns and for anyone who's.
Are you getting your resume?
No. All right, so what's Sora? It's kind of a blue sky moonshot research project in the research labs. Microsoft Research, in Microsoft Research, you can still do this kind of forward-looking research that's not inference or not connecting to product lines. So in fact, there's no Microsoft products or product lines or plannings has anything to do with wireless. Microsoft's not running any wireless networks, not producing any wireless equipments, but we, as a research labs, we want to look at things that we are very, very interested to see 5-10 years down the road, what would be important. So we started this project about a couple of years ago. With the thinking about how can we do better to advance the state of the art in software radio. Can we do full rate, full speeds 802.11, for example? Can we use the latest computer architecture to do that? So we have some major progress at the end of 2008. We found a way to build a new way of doing software radio. I think that the first demos, a full rate Wi-Fi 802.11 A and B and G. in pure software. Everything is total software. Obviously, I'll talk more about that in this slide. Is actually one of our key, proof is that we are able to interoperable with the commercial Wi-Fi card. That prove a lot of the speed, the feasibility of these platforms, and there's no corner has been cut. What's a software radio? Probably don't need to talk about that in this lab. So it's like we all know about what a software radio is. So I'm going to skip these slides. Yes. So the point I want to make is that software radio is actually an evolution. So and also many of you probably have similar vision as well. So if you were talking about a radio as multiple components or multiple layers, going from antennas all the way to applications, these on different time, many of these things that maybe used to be implemented in hardware is going to turn into software as a matter of time. So right now, it's probably, if you look at radio system right now, the application and network part is probably already implemented in software running on general purpose computing device. And I think what happens right now is that the baseband is turning, the baseband turning software. There's a lot of evidence on that. Maybe in the future, sometime in the futures, we'll see intermediate frequencies and also even closer to the radio frequencies high will be turned into software. So I'm going to focus on now so what's feasible today. There are multiple choices that if you want to build a software radio. Most people, especially from the wireless industry or wireless communications aspect, will choose to use FPGA and DSP. So even though the advantage of this FPGA or DSP platform is the speed and performance. It actually allows you to implement high-speed wireless systems, although it does come with some disadvantages about, it's very difficult to program directly in FPGA. You need to have some very efficient tools, and those tools are not very easy to develop efficient tools. A general purpose processor, like a CPU, has the other set of trade-off. It's very easy to program. It's it's very easy to find developers that can work on CPU. Then there's arguments about CPU is probably slow. Now I want to bet on the general purpose processor based software radios for the following reasons. I want to argue that the flexibility and scalability is better on the general purpose processing architecture due to there's a mature industry support moving very fast forward onto that. The programmability is always better. That's kind of is a general consensus. If you can do it on CPU, of course, you can do it in the general purpose PC. Of course, it would be better for development. Convolutional PC is cheaper, just pure because of this market size. They have driven the cost down on convolutional device. Now, of course, the fundamental question is that, at this point, can a general purpose CPU does its jobs? Well, it really depends on what jobs are we talking about, right? So we want to be able to support high-speed wireless at the range of like tens to hundreds of megabits. We're not talking about low-speed or narrowband wireless systems. That's probably we all know that easy to do on the PC already. So we want to see whether today's industry state-of-the-art wireless systems, like Wi-Fi or 4G, LTE, for example, whether we can use a general purpose PC to implement those wireless systems, and possibly with multiple antenna, right, MIMO. Now, looking into high-speed wireless, and we do some back of the envelope calculation, we will see that it actually have really, really challenging requirements on the platforms. It has to have a very high system throughputs. Just based on pure calculation. If you take a 20 MHz channel, you want to support 20 MHz channel, and you assume you only have 8 bits I signal and 8 bits Q signals, that gives you about over a gigabit per second. So we are not even talking about oversampling here. Now, if you want to add multiple antenna or doing a wider band channels, so this number quickly multiplies. Computational power. So wireless system is all about signal processing. It's all about computations, number crunching. Especially if you want to increase SNR, and you will require more computations out there. So some examples about, for example, waveform decoders, LDPC. These are all well-known decoders that needs very, very intense calculations. Somebody do some estimations. We are not a communication background, so we don't have a good estimates about what's a wireless computation require. But I'm seeing some reference saying that if you want to do Wi-Fi types of wireless decodings, you probably need like close to like tens to hundreds of gig operations, mathematical operations per second. And some protocols also have a very restricted timing control. Like for example, 802.11 types of MAC, it requires you turn around to have the packets acknowledgement or RTS, CTS type of turnaround within, a few or tens of microseconds. So that's really, all this adds up to a very serious demands on the systems. USRP and USRP2, that's, you all know that there is a general purpose PC-based software radio systems. It's one of the most popular software radio systems out there for research purpose. Signal processing on the CPU, there's a large bodies of existing softwares that's called radios out there. But it does have some performance issues in terms of is the platform choice of interface to PC. Neither USRP, neither USB interface or gigabit Ethernet will be able to satisfy the requirements that I just talked about. So the best throughput I have seen in the literature is probably around megaseconds. So it's still not able to do Wi-Fi or definitely not able to do LTE types of high-speed wireless that we set out to do. And well, what is our platform then? I think we have a significantly better software radio platform compared to USRP. It leveraging the current standard PC architecture, like multi-cores and PCI-Express. I'll talk about that. And we also have serious innovations in the software part to speed up the signal processing on the PC. So Sora as a system turns a commodity multi-core Windows PC into a powerful software radio, be able to do like Wi-Fi or LTEs in pure software. So what exactly what we do? So we build our own interface card. It's this card puts into a multi-core PC. There's a commodity multi-core PC that we can buy. We can buy it on the market. Connects that with RF front end, analog or digital RF front ends that generates the IQ signals. It takes the IQ signals to transmit on the over the air. Adds our software, then it becomes a software radio systems. Now, so how do we meet our challenges, the technical challenges that we have our layout? For example, high system throughput, high computational power, and accurate timing control. The high system throughput, we choose the PCIe interface card because it is just standard in most PC, and it is able to deliver over 10 gigabits per second. So that's a well-known fact out there, and it's a good interface of choice. High computational power. We observed that this multi-core wave, we all know that it's now in PC industry, is a sea change and moving from single core to multi-cores. Right now, if you want to buy a PC or even a laptop, it probably comes with 2 cores or 4 cores. So in a couple of years, probably like when you go buy a PC, it probably comes with 16 cores. Our software radio inventations of any physical layer shall take full advantage of the multi-core architectures. We do a lot of algorithms optimizations to fit into these the latest CPU architectures. The last one about accurate timing control, and we use core dedications. The idea is that, well, once we have a multi-core, once we accept the fact that the CPUs come with multi-cores, we can reserve some of the cores for software radio application. And then we're able to solve many of these real-time problems by having a total controls of the CPU and not let other tasks in the operating systems to interfere with the software radio task. The hardware architecture that I just mentioned, with this high-speed interface cards, we're able to deliver the type of throughput and latencies that we require. Now, although these cards is a little, there's a lot of electronics, even an FPGA here on this card, but there's no signal processing happens here. The purpose of this interface card is to create a bridge between the RF front ends and PC's memory. The purpose of this card is to take the digital IQ signals after the digital converters, and take this signal and ship it to PC's memory as quick as possible. And also, on the other directions, whatever waveform generated by the CPU, stored in PC's memory, and ship it to this cards and send it at the right moment. Now then, there are, I'm just repeating what I said before, there's some software innovations here happens in the multi-core. So all the signal processing actually take place on the CPU. So I just give a few examples about how do we do file layer implementations that be able to meet the requirements of wireless signal processing on the CPU. One example is that we explore large high-speed cache memory into PC's architectures. So implementing signal processing in the CPU always is very different than doing that on FPGA. Doing that on FPGA is probably you do computations, based on computation. But with the high-speed cache memory in the CPU, you can actually do a lot of pre-computations. So build that into some kind of lookup table. Then you can trade memory access for a number crunching. Here's one example, simple example. Convolutional encoder takes the input data, a stream of input data, then you have each of these, and then they will generate two output data streams. If you want to do direct computations, there will probably need 8 operations per bit, right? And if you look at it in a different way, so there are, for each bit, there's all that many possibilities, right? Each bit of either 0 and 1, and then you calculate all the possibilities of doing this. You can come up with a table that have all the possibilities of incoming data and mapping to the outgoing data streams. So if you build that tables, you can actually build that table. The size of that table is now 32 kilobytes, but it easily fit into L2 cache. And then now doing 8 bits together only 2 table lookup. Well, implementing all the 802.11's file layer algorithm, we found that more than half of the algorithms can use some form of speed up like this. That gives you somewhere between 50% of improvement to like 22 times of improvement. So that's one example. Here's another example. In modern CPUs, there's many wide vector, single instruction, multiple data instructions out there. For example, Intel CPU or AMD CPU, they all have the instruction set like SSE. If you utilize that, you can exploit data parallelisms in PHY, and things like FFT or IFFT. You can use this kind of instruction to do speed up. And we found there's many file layer algorithms can use this kind of speed up to give you up to sometimes give you up to 50 times speed up. So multi-core is another technique that we use for giving any multiple stage of file layer implementations. You can break those into pipelines and putting different pipelines on different CPU cores. And of course, we need to have some software, highly efficient software mechanisms to connect them and be able to do this in parallel. These are another technique. Core dedication, I just talked about, so this is more like the operating systems mechanisms that we derive that allows you to guarantee computational cache memory resources for software radio tasks, to be able to achieve microsecond layer of timing controls in the general purpose operating systems. For example, we implement this on Windows XP without even changing the kernel modification, we can do all this in the device driver layer, be able to achieve the necessary real-time support for our software radio. So we don't even need a real-time operating systems for that purpose. So putting all this together, we are able to implement and run the 802.11 all modulations and all full rates up to 50 megabits per second, 64 cores, with one Intel eHarmony core. So what is Intel eHarmony core? That is the current generations of Intel CPU's architecture. For example, the Core i7 type CPU is using these architectures. We use actually the slowest Core i7 900 series, 2.6 gigahertz, only using one core, be able to do that. And by the way, Core i7 comes with 4 cores. LTE, we implement the half of it, the uplink share channel, LTE 5. We'll be able to achieve 43 megabits per second in the 20 megahertz channels using 1.5 cores. So again, the same type of CPU. It comes with 4 cores, so we use only less than 2 cores for this software radio task, and we still have other cores that allows you to do other things, normal Windows process and other jobs. Programming, we have our own more programming models. I'm not going to go into much details here. People, if you are interested in the programming, then we can talk afterwards, or you can find some further documents in our website.
Can you give us just a general idea about the program?
Okay, so all right, so
what is involved to program this?
What's involved for 2 programs is basically for 2 parts. So for the file layer is the Sora software infrastructure will provide all the drivers and the environment support, so that your programming model usually is like this. With the hardware plus Sora software, we put those IQ signals directly DMA into some DMA buffer in the memory. So we tell you where are they.
So that's FPGA essentially?
No, this software is running on the PC, so you use C program.
But what comes into the DMA?
That's the hardware and the software driver, the software driver. So that all the IQ signals will show up in DMA buffer somewhere.
So it is not necessarily FPGA, that's a currently actually that's not
it's PCI-Express bus.
It just take the samples from the radio command and transfer that to the PCI bus to the network.
Your current implementation is that?
Yeah. Currently they were using the Vertex Spot, so they have the FPGA code, so we use that. So
PCI-Express core you need.
So we need the FPGA for a few purposes. I mean, we need that as a driver to drive the PCIe bus. We need that as a way to do the DMA, to copy the digital IQ signals to PC's memory. So those parts are all, I mean, is part of the platform. So you don't need to worry about those. You can think of this. This will magically, those IQ signals will show up in PC memory with less than 1 microsecond delay. So whatever comes into the air will show up on PC's memory. So we'll give you the pointers. So now you need to write the whole. I said this is just one part decoding the receiving train. You need to write a file decoder, and then it shows up as a frame, right? In this, you can have an interface to the upper layer that does that's the the MAC and the IP and networking and all above.
So which of these are table lookups?
Which are these table lookups up to you? That's table lookup is optimization techniques. So you write your own. Usually it's like this. You write your own algorithms. This is just an example. Like for example, you move the DC and do some filter and do some demappers and decoding or whatever, and then you tell us using some language, programming language models, that which part that can be break. So for example, some of these part probably you don't want it to break. Some of them you can break, and some of them you can break. Then you can decide how fast it is going to run, and then whether this should be put into one core, this another core, this another core, and so on. And for each of these modules, this always is a mathematical functions, right? Then you will see whether you want to do direct computation. If you want to do direct computation, if very slow, then there's tools to generate lookup tables to replace those computation with lookup tables.
Those tools is what you provide?
The tools that we have some tools, yes.
And you also provide the tools for connecting cores?
Yes, yes.
This is actually where you provide a program model, like they call API functions. So it's not virtualized to drag down not like this, but we could do that later, but now it's just a program model APIs. You just call APIs. So like you're reading, you do not directly read from a point where we actually provide that C++ object they call the stream. Actually, the model stream, you read a stream, what you get is a array of IQ samples. Then you further program, and you put that into any FIFO. It's just kind of buffer. You put that in buffer. You have APIs. So you declare, put one sub-pipeline, put in the sample in there, whatever, process the data, and the other end is some other process from the data. Basically like this.
Right. So you really need to think in that way too. So for example, it's not possible that if you write a piece of mathematical function that we will automatically convert it into lookup table. That's not possible. You have to think in that way. So you say that, well, these mathematical functions can be implemented in some kind of lookup table. Then there are some programming constructs that can help you say that how big a table with what are the rows and columns, and how do we generate the each of the elements. So once that we build up the table, put the cache memory somewhere, then you can do table lookup. So also about this vector one library is also the same thing. So when you do your write your algorithms, you'll see that this algorithm has a lot of vector operations. So you want to do multiple of data at one step, then we provide the language constructs for you to express what you want to do.
Are you going to provide some library to implement some already optimized?
We have released the sample code for 802.11 ABG. So that's actually a lot of things there. For example, the entire OFDM, entire vertebrate decoder. So that's all provided as a sample code in source code. So you can use that as to build. You can take those out and to build as a component to build your own file. You can modify it for you to shoot your file layer. We also provide a provider. Provider means that I'm going to run these whole things, and we also have tools like, for example, takes all the digital signals, so store it in the file, and then play it back. Then you can verify whether your implementation is fast enough, right? So one way is to, if you're not fast enough, then you will see what I'm going to do, right? Whether break this into stages, running a different core, that's one way to speed up, or you see whether these algorithms they need to spend more time to optimize it. That's what the provider does. We also have some oscilloscope, oscillometer, that's when you have the digital IQ signal, will display graphically. Like for example, its phase, its constellations, and the decoding results, and to use that as a debugging tool.
Yes, here, your example, and all components purely in sequence. Do you have some example that some component is not is purely in sequence? Here, what I mean that if I have some
Yes,
feedback,
there's some loops and feedbacks. Yes, you can write those. You can.
For this component, if I implement it on a different core, it will such as one component is one core and feedback on the other core.
Yes.
Do you have
how to? Yeah, it's typically you need to do some synchronization among among threads. So I think it's already provided mostly in your system. You can using either shared memory flags or events, depends on how critical you are. Something then it's already there. So that's the good thing. You using the general purpose of operating system, so everything is there.
Yes, I mean you write your own modules and you decide where to put in the core, right? And then there's some programming mechanisms allow you to connect all these together. For example, FIFO is a very well-known mechanism to synchronize threads between two cores, as Kun just said. There's other well-known operating system mechanisms that allow you to synchronize coordinates between two threads running on different cores. Then you use those, right? You use those, and then you run through the profiler and see whether all these be able to meet the timing constraint.
How about some signal processing in RF domain? That's all baseband.
Oh, this is all baseband. This is all baseband.
I'm talking about the RF and the processing, like the frequency synchronization, like Encoder and then transmitter. So how?
This is
Well,
all.
we can do it only after you do the digitization. So
This is all after you digitize, right? And this obviously this has to
So
be
the
digital.
frequency synchronization, those stuff are done in RF module.
No, but you can do no. I mean, you can. If there is a frequency offset, you have to do it in the basement. Right? You have to ship that.
So you can.
You have to. There is no way for you to influence that.
So what happens if you have some frequency offset?
If it's small enough, you can compensate in the basement. But if it's too big, right? If your oscillator is so off that you can't sample it properly, then you're.
Well, what happens when you change it?
No, so it's the same. Transmit is a problem for the receiver, right? If you're off, the other guy has to hunt it. Right?
But that's what I would already.
It all depends on. I mean, it all depends on sampling, right? If you sample enough, you can do it.
Right.
Just think if you sample 0 to infinity, right? Then you don't need the RF synchronization.
So actually, this is if you really want to do the analog domain, so that you can take them and then figure out what is the right frequency point, and you just feedback to the hardware. Say, please, just bring it off that to the design.
So as part of the platform, we also provide some interface to allow you to control the radio. So at some point in time, you could, here, for example, here you can call some APIs, control the radio, ask the radio to do something, right? And that control path, we also measured it is within 1 microsecond. So it's within microsecond, you can control the radio to do something.
You want me to do that? So actually, we abstract video. So we just take any video and abstract that to a abstract video that contains a X channel, K channel, and virtualize the control registry. So I have a design for example. registry number 0 is to how you set frequency offset. So we have all the standards. So we have a specification on that. So you implement the radio and want to connect to the Sora, you need to interpret these operations on these virtual registers and translate these operations to the setting sequence of the real radio chipset registers. So that's how we did it. So we have a common API. You just say, I want to set the frequency and send the write to the virtualized register. Then under the radio controller, we do that for you. So in this architecture, you can translate. So you can replace one radio without another radio without changing the software.
Yeah, exactly. Yeah. So right now we support the wireless WAP protocol and the USRP protocol. Yes. So they are, to us they are the same.
So right now, since this system works fine with the direct RF, everything is AUT. This in the baseband digital.
Yeah, in the baseband digital.
And in fact, the future are doing some digital domain. And also, in case you need to do the IQ imbalance or frequency offset, in fact, you can do it in
baseband. Yes.
Yeah. But the thing is, if somehow you need the IF then the RCB board, you may need to do more function instead of just
so
right now.
We just put that to the radio part. So my position is that the radio board should provide such functionality to, for example, adjust this IQ imbalance. So the RCB just plays a role that just connect to take the command and transfer command to the radio, and the radio interpret command and do something the radio adjustment and so on.
Yes.
So does it support full duplex in the RF and the baseband as well? Like, for example, a daughter card, full duplex.
Full duplex.
Yeah. For example, can you have split course transmitting?
One course transmitting, one course receiving, right?
Well, if the radio friend supports it, yes.
So DMA is the duplex, so
Yeah.
full duplex, but unless radio broadband, yeah, support that.
Yes, if the radio front end supports that. Now this is a receiver chain, right? The sending chain is also the same. So we tell you when you generate the waveform, where do you put it? So once you put it, the platform we're going to ship it out. Now we support up to 8 channels. So if you want to do MIMO, you have 8 radios connect to the RCB board. Then we'll tell you that where are those. You find there's 8 buffers. Then you do your algorithms there to take all these 8 buffers and do your decoding. Right? One philosophy is that we don't want to add more intelligence in the RCB, in the controller board. We want to make this a pure software, see how far we can push. And on the engineering point of view, you can also do something like add logics and things in the control board, but that's not, we really want to see all the base is a pure software, and the radio has its own analog things that need to take care of, and then this interface can have a high throughput between these two and a very, very low latency between these two. And the software be able to control the radios, it will have a very accurate timing control. So that's all this platform trying to achieve. So the benefits, well, you can beat a commodity platform with C program. It's a very familiar environment that you can use all the tools that in a general purpose OS that provides you. So for example, we use the Video Studio. That's a convenient software development tools, C programming tools on Windows. This solves productivity. The Wi-Fi's 5 implementations takes 2 students 2 months. One of the students come in without any backgrounds on wireless communications. We tell him the standard of Wi-Fi 5, break that into blocks. Each block is mathematical transformation. So he would just take these math functions and try to program it. But he's a very, very good programmer, training in computer science. So he's one of the very best computer science students. So he's been able to convert this into implement those in the platforms, and two students work together and then finish that in 2 months. LTE PHY implementations, well, that's another way around. We have students coming from a communication school that has he already know the LTE standard. He has done a little bit of FPGA programming. So get him over here that he learns the C programming. There's a little bit of background, but not very fluent in C programming. So he tried to learn his way through and be able to implement this PHY in 4 or 5 months. So all this shows that given these environments, you can just really be able to produce these things very quickly. The oscilloscope, it's actually one student's 2 weeks. All the IQ signals in memory is all about graphical user interface programming. And there's a lot of tools that allows you to do that. It becomes a wonderful research tool. I'm going to show you 2 examples. One of our MobiCom work and one of SIGCOM works using the Sora as a way to allows us to facilitate us to do wireless research fairly quickly. With the time limitation, I'll probably just quickly go through one example. So spatial multi-access. This one of our MobiCom work enables spatial multi-access in wireless LAN. The idea is without spatial multi-access, you have all these stations have 2 antennas. Even though this has AP may have 6 antennas, you probably only get 2 times of capacity. But with spatial multi-access, you probably can get 6 times because they have all these stations can transmit at the same time. Right? So obviously, in order to do this, you need to think about how do we do distributed random access, do asynchronous simple transmissions, how do we coordinate all these access. Again, there's a lot of file layer work and map layer work as well. So there's some file layer design, there's some map layer design. Without these two, it will be fairly difficult to prove, evaluate all this approach in the high-speed wireless LAN settings. So with our tools, we'll be able to do that. At least the implementation pass in 2 months to have some good results.
So you raised the frequency synchronization on the previous slide. Can you show that again? So what if you have different units with different frequency offsets?
So the baseband, so as long as it's a frequency, it's not too big. So the idea is that currently is that we do this nullify and cancellation, basically infinite cancellation. You can say that wave cluster, distributed wave cluster structure. So actually you cancel one layer by another layer. So, but actually each layer can have different, of course, frequency offset. It doesn't matter too much. But the cost is
the range is limited by what the sampling rate is actually. The range of frequency offset.
Yeah. You cannot be too nice. But the limitation for that is that actually have the energy as a non-loss because they just do the calculation.
But you don't handle the frequency offset. You just allow for different frequency offsets in this structure.
When you do the calculation, you do not need to. When you do the calculation, you still need to model this frequency offset, but you can model the frequency offset individually, so you do not have you do not have to that these two standards synchronize together. So that's it.
So I suggest to take this offline about this wireless research, and obviously there's a lot of discussions here. And I just want to use this to make a point about how our Sora can help to speed up wireless research, right? So
I didn't warn you. Our talks are usually twice the length.
Well, fine. I mean, so maybe we can discuss this afterwards. Another example: fine-grained channel access. The idea is that when this wireless LAN gets higher speed, the MAC overheads becomes bigger and bigger, and then it's really the useful airtime with data rates will decrease. So how do you do that? So maybe we find out one way that you don't use up all the 20 megahertz channel. You want to reduce the channel width for each access. Again, there's a lot of file implementation has to happen here. And again, so I'm sure many of you have many questions about how this can be done. There's a lot of discussion. So hopefully we can do that afterwards. But I will just prove a point that in order to do this kind of experiments that allows you to do sub-carrier things, that you really need to be able to do a lot of experimentation on the PHY and OFDM. Our tools allows us to quickly implement something within a couple of months. It's very difficult that without such a tools, it's not possible to do in USRP. And again, experimenting and evaluating in the real environment does give a lot of credibility of our research. So it has been highly regarded in the academic community. Won some demos, speculated by paper awards and such. And the next issues of CACM it also features this paper. Tell you a bit about ongoing work. We have released the 802.11 APG, I just mentioned. We are about to release the 11N MIMO. Capabilities. We hope to provide better programming models and tools to continue doing that. Since we have the platform and we probably are the best people knows how to use these platforms, we try to leverage that and do some very radically new wireless systems. Like for example, gigabit wireless. I want to see whether we can achieve gigabit wireless on general purpose CPU and a general purpose PC. If we cannot today, and see how what's the gap and how to bridge the gap and so on. And we also this research project also brings a lot of research problems to other communities, like computer science research problems to operating systems, parallel computing, and so on. So let's see. Let me try to conclude this talk by making some statements. Software radio is here. Before we start these projects, I think people's perception is pure software radio is a long way from reality. I mean, at least PC based. Many people have the perception of CPUs not fast enough today. Maybe in the future, but not today. But our work actually, we believe our work actually challenge that perceptions. We show that today's fastest PC can do the fastest wireless, at least at the baseband level. And we predict a commodity PC in a couple of years, for example, in 2 years, we can probably do gigabit wireless. Maybe we will reach at some point in time, it is not necessary to implement the wireless baseband in software, even for the even for the highest wireless communication. If you reach some points that the Moore's law will just exceed the wireless communications computational demand. It's obviously that I believe there's a disruptive potentials here. Software radio enable a potential paradigm shift in the innovation models. It allows you to have rapid prototyping of your wireless ideas, and allows every school, every labs to try out new algorithms. And Glue Radio and USRP does the initial works to open up the wireless world, so allows everybody to experiment the wireless communications. And we hope our work contribute to that directions that open up the wireless worlds for everybody to experiment with. To that notes, we open up our software radios platforms for academic research. It's a free software under Microsoft research license. We authorize a third party OEM to build the RCB board. Because that's still have some cost involved to building that piece of hardware. So the procedure is you're going to use your own multi-core PC, which is not a problem for many schools. You find some third-party radio front end. Right now we support USRP, we support SWAP. We find any other radio front ends that the system can support, we support that as well. Then you get a software from us, free software from us, and get an RCB from some third party. And then you build up a very, very efficient, high performance software radio. There has been over 20 schools been using these platforms today. Many of them in US, actually majority of them are in US schools. Here's my last slide. It's my personal opinions of software radio outlook. We're already seeing that there's a lot of software radios in wireless research, so that's already a fact. There'll be more and more software development environments and tool chains. Perhaps the software radio coming out party is white space. It's still very difficult to do wireless in the licensed band because of these constraints of being licensed. But the unlicensed bands, especially in white space, there's no standard, there's no firm standard yet. There's really unexplored territory. Software radio allows many people, many schools, many researchers to explore things in white space. So that's probably one coming out parties. My dream is to have a wideband transceiver, 100 megahertz or above. Our expertise is in software, not in RF. So we look up to other schools and other companies to providing the transceiver, the RF transceiver capabilities. And this is probably happening. IT industry marching into wireless communication. The software radio allows them to do that. So 5 years ago, you asked me, I don't see how Microsoft has anything to do with wireless. But today, you see that Google's, Microsoft's, Intel's, IBM, these companies are marching into wireless communications. The white space is pushing by Microsoft and Google's and Philips and HP and Dell, all these traditionally IP companies. They're probably a couple of years ago, nobody would believe they have anything to do with wireless. But today, this is maybe happening. Okay, so that's the end of my talk. So I run a little bit over time. So sorry about that. Any questions?